The final circuit that I'm going to discuss in this series of network analysis with networks in resonance and electronic network analysis is Norton's theorem. Norton's theorem states that any two terminal networks can be replaced by an equivalent circuit comprising a constant current source in parallel with a single resistor. So the constant current source was discussed in a previous video, and I'll put the link in the description and a little box to click on at some place in this video, so we can refer back to constant current source in a separate video. So as the law is saying, the rule is saying, we can take any network and we can replace it with a simple equivalent circuit comprising of a current generator and a parallel resistor, and we would call this a constant current source. A constant current source would be otherwise then known as the Norton current, so IN. Okay, this is equal to the short terminal circuit, the short terminal current of the network measured through points AB. So as we see here. The resistance value would then be known as the Norton resistance. So you're kind of seeing a wee bit of something similar to what we saw in the CCS video, the constant current source video, but we'll just label them now Norton for the Norton current and the Norton resistance respectively. So the Norton resistance is equal to the resistance of the network measured between the points AB, again here, but looking into the network. And what we've done is we've replaced all sources by their internal resistances. Once we go ahead and work out the value of Rn and In, we can go ahead and determine a range of circuit quantities, which we'll now see once we've taken a quick look at the simple rules. So before we take a look at the actual problem, these are the three general rules. Step 1 is to remove the resistor in question. That's the resistor that you want to know more information about, whether it be current or voltage relating to that particular component. So we would remove the resistor in question and replace it with a short circuit. This would allow us to calculate the Norton current. Next step would be to remove the short circuit that we placed in step 1, and we would replace all the sources with their internal resistances. This would then allow us to calculate the Norton resistance. With IN and RN calculated, we would then go to step 3 and draw the equivalent circuit that we saw just a moment ago, and we would put the original resistor, the resistor in question, back across terminals AB. This will all come together once we look at an example. So the example we're seeing here is to use Norton's theorem to calculate the voltage drop across the 6 ohm resistor. You can see from this we have a series parallel network. Okay, 10 ohm resistor being in series with a parallel network going down through the 15 ohm resistor and this connection between the 4 and the 6. And we have an 8 volt DC supply. So starting with our first step, the first step is to remove the 6 ohm resistor in question. And we're going to replace that with a short circuit. If you've seen the Theorem video, you'll notice that it's the opposite way around. The procedure for Norton is the opposite. So you can refer to the Theorem video if you want to solve problems that relate to using Thevenin's theorem. All you need to remember is that Thevenin does it as an open circuit and Norton does it as a short circuit. So we've replaced the 6 ohm resistor with a short circuit between terminals A and B. And what we can do now is we can go ahead and work out the battery resistance. That is the resistance as seen from the perspective of the battery. Looking into the circuit. So from this we can see, and I'll call this R bat, that the resistance is going to be the 10 ohm. The total resistance from the battery perspective is the 10 ohm resistance in series plus product over sum. So we have, again, product over sum. And that's because of this relationship here. The 15 ohm and the 4 ohm resistors are in parallel with each other, and the 10 ohm resistance is in series with the parallel network. And when we calculate this, we'll end up with a value of 13.16 ohms. So we've calculated the battery resistance from the perspective of the battery. And now what we can do is we can work out the battery current. We can simply use Ohm's law, which means we can take 8 over 13.16, and that will give us 600 milliamps, or 0.6 amps. Now if you recall, what we're trying to do in this step here is we're trying to calculate the Norton current. We've just calculated the supply current from the battery. I'd like to take a moment just to refer you to my lessons that I've used in the past, and that is always draw your circuit, because then you can label stuff and it'll start to make sense. So we've calculated the supply current, which means that if you consider what the Norton current is, it's going to be the current flowing through this branch of the circuit right here. The Norton current is going to be, whoops, that's Microsoft trying to do smart things for me when I didn't want it. The Norton current is the current flowing through the 4 ohm resistor, down through the terminals AB, and back to this terminal here. So the current is actually splitting at this node here, and then rejoining at this node. So, how are we going to solve the Norton current? We're going to use the current division rule. And we're going to take the supply current that we've just calculated, and then we're going to multiply that by the ratio of the split between the two resistors 14 and 15. And I know I repeat myself, I don't care, it's good for you to hear repetition. If you know this already, then good. But when we're dealing with the current division rule, the resistor that we want to know about, the resistor that we want to know the current through, which is the 4 ohm, well, we want to know the current flowing through this branch, but we put the other resistor on top. Okay. So calculating this, we'll end up with 488 milliamps, or 0.48 amps. So now we have calculated the Norton current right here. Moving on to step 2. Step 2 then discusses removing the short circuit that we just applied across terminals AB, and then taking the 8-volt cells and replace those with a short circuit. So as you can see, I've removed the short circuit here, and I've removed the battery source on the left hand side and replaced it with a short circuit. So you should now hopefully recognize that when we're looking at calculating the Norton resistance, we're looking at that from the perspective of the terminals AB, looking this way. And one of the things that I like to try and help people understand when they're thinking about series parallel networks is, what would the current do if we applied a current from A through to B? Well, we can see that our 4 ohm resistance is in series, and then we have a split. Current travelling through the 10 ohm and the 15 ohm resistor, and then rejoining at this point here. So we can go ahead and work out the total resistance, simply as Rn is equal to 4 plus, and then again, product over sum, which will give us a value of 10 ohms. Now that we've calculated the Norton resistance and the Norton current, we can go ahead and draw our equivalent circuit. So again, I always emphasize to draw your circuits as you carry the network reductions, the analysis, whatever it is you're actually doing. I always encourage students to redraw these things. Okay, it makes your thought processes much clearer, much easier. It's more engaging as well. Now let's consider the redrawn circuit having placed the 6 ohm resistor across the points AB. We were interested in, once you've done this circuit by the way, once you've drawn this on your page, I would encourage you to go right the way back to the top of your page and consider the question. Using Norton's theorem, which we've been doing, we're expected to calculate the voltage across the 6 ohm resistor. So if we want to know the 6 ohm resistor's voltage, well, we have a resistance, let me change that pen colour, R equal to 6 ohms. We want to know the voltage. We're going to have to find out the current, aren't we, first, before we can calculate these using Ohm's law. Again, you should recognise, hopefully, that we can simply apply the current division rule. We have a source current with a magnitude of 0.48 amps, and then we have two resistances. So there's going to be a split in the current at this node here. So using current division, and I'll call this I6 ohms, that's going to be now equal to the source of the supply, in other words the Norton equivalent circuit. Don't be tempted to go back to 8 volts, okay, or anything like that, anything like your, no, beg your pardon, not 8 volts. Don't be tempted to go back to the supply current calculated at the beginning. In this part of the calculation, we are now only considering, in this redrawn circuit, we're now only considering the supply of the constant current source. So be very careful. I see students make this mistake all the time. So we take our Norton current and we multiply it by the ratio of the split. I'm interested in the 6 ohm resistance current, therefore I take the 10 ohm over the sum. And that gives me an answer of 0.3 amps, or 300 milliamps if you prefer. So we know now the current flowing between terminals AB, which means that we can now calculate the 6 ohm volt drop, which is going to be 0.3 times 6, which means that the resistor 6 ohms experiences a volt drop of 1.8 volts. And that's Norton.